Any questions? The last thing we did,
Car on slope.
going around the curve. All right, we finished that.
Yes.
All right, so in essence, all the, oh, I guess one other thing. I have a test 1B written down for Thursday. That was not you. Only Ibrahim.
Okay.
Yeah, I think that was for 251. All right, so all the circular motion problems, matter of fact, all the problems from chapters 4, 5, and 6 go through the exact same process. It's just a matter of different context. So, we're going to go through the same process as we've been through many times. Force diagram. Not the scale. What are the forces acting on the Earth and Sun?
Gravity. Makes sense. Gravitational.
There we go. Why not gravity?
Because
Anybody can chime in. You don't have to sit there and watch Lee look uncomfortable. Yep, there you go. And why not wait? Yeah, it's not a hand gesture thing.
There's two different gravities, right? Or, yeah, so there's two different gravities, you can't have you can't have a consistent weight, right? Because like one of them is dealing with mass times gravity, so yeah, so weight is mass times gravity. Okay, so weight is mass times gravity, and so the
Well,
gravity.
you just did. Mass times what?
Mass times gravitational force.
Yep.
Mass times force due to gravity.
So we want to help Ibrahim out, or just watch him?
Acceleration due to gravity.
There we go.
Okay. And so the
MG is just a whole lot easier.
mg, and so that varies depending on the sun and the earth, right?
What is little g? I mean, he's already said it, but say it again, somebody.
acceleration due to gravity.
All right. And upon what does that depend?
How strong the gravity is?
Oh, on the much bigger object, like me, and then the earth. The earth has gravity.
Okay, it depends upon the other mass.
Right.
We're going to generalize it. The other mass. And
Location?
yeah, in generalizing how close you are to it, how close the centers are to each other. Yeah, perhaps a little bit too generalized, but good enough for this. All right, so I could use mg for this, except I don't have a clue what little g is. But it's still not weight. Weight is when you've got the small mass. I think you're getting towards it, when the small mass is near the big mass. When you pretty much pretty much guaranteed that little g is constant and it's a known value. So we have to use the generalized force due to friction, or, wow, force due to gravity. All right, what else?
Tension.
Because of that long rope between the Earth and Sun.
Yeah, exactly that one.
Let's just, for the sake of this, let's simplify it. Let's just assume that it doesn't exist.
Okay.
All right.
I think that's it.
I think that is it. Normal force requires contact. Friction requires contact, or if you're dealing with air resistance, it requires air. Tension requires a rope or chain or something holding together. There is no hand of God, and, well, we've got the gravitational force. All right, so that's it. We will assume that the mass of the sun is 1,000,000 times more than the mass of the Earth, which is about right. What's the direction of the acceleration of the Earth as it goes around the sun? And let's assume circular orbit.
Towards the sun.
Yes. So how do you want to set up the coordinate axes? Or axis?
One in the direction of acceleration, and the other one perpendicular to that.
Okay. I guess in my mind, they're just going around like that. All right. Next.
Oh, why aren't we using I-hat and J-hat?
Because the Earth is traveling in a circle, I could use I hat, J hat, and just do a snapshot at that spot right there, and no problem with that. I was thinking if we consider the Earth going around the sun, the coordinate axes are actually changing with it.
And why'd you put like the hat, so V hat.
V hat would be a unit vector in the direction of velocity. And negative R hat is because R hat is away from the center, and negative R hat would be towards the center, with the sun being the center.
I don't think we need to decompose anything.
Okay, because if we don't need to,
I don't think so. Because we have the force of gravity going towards the sun, and then we just have the coordinate going with the velocity. The V.
that's a V there. This actually is irrelevant, because there are no forces in that direction, so the equation of motion in that direction is going to be the clever 0 equals 0. So
We'll only have one equation.
we'll have only one equation. We don't need to break anything up because our only force is in the direction of our coordinate system. I felt like you were getting towards that, but
Yeah.
it didn't
I
feel like
think
it came out that way. All right, so our equation of motion.
Oh, I see the,
F, is that F1?
F sub G.
F sub G. Minus F sub, what's the other one?
That right there?
Yeah,
That's F sub G.
just the same thing.
So you're proposing F sub G minus F sub G?
Wow.
When you're doing equations of motion, you're doing the equation of motion for an object. You're not doing it for the system. So I have only one force acting on the Earth, so I have only one force there, so F equals.
To something. MG.
And it is centripetal acceleration. If you did it in G, we're still stuck in the position of what the heck is little g here? All right. What's next? Okay, do we have an independent formula for any of this?
The acceleration, centripetal acceleration, no.
Okay.
V squared over R.
Chance for someone to show off here.
Equals GF.
All right. So using this partly as an introduction into, this is the same type problem as we have been dealing with, and it's actually slightly simpler, but we do have an independent formula for this. Now, as we talked before, we have this little n, little g that we can use if we know what little g is, but we don't know what little g is. When you're dealing with outer space, typically probably shouldn't be using that unless you're trying to find little g. Let's think about upon what it depends.
How close you are to the other object?
Okay, so the closer you are, the greater the force or less the force?
Greater.
Okay. Can you think of something where the closer the things are together, the less force it would be?
Not correct.
Okay.
I was thinking magnetism. I was thinking like magnetism.
The closer you are to a magnet, the stronger the force, or the closer magnets are to each other. At least that's my experience.
What if they're opposite?
Pardon?
What if the magnets are opposite?
Well, it's a matter of if they're of opposite signs, you get a much stronger pull.
Mm-hmm.
If they are the same sign, or bad wording, if they're both north or both south, then it's a greater repulsion the closer they are together.
Air.
Pardon?
Air.
The closer air is to each other, the weaker the force. Wow, I did not know. Rubber band. If you put your fingers on a rubber band, as you stretch it out, it's a stronger force. As it comes together, it's less of a force. Or elastic materials. All right, so the generic formula, as R gets bigger, the gravitational force gets smaller. I'm gonna adjust this in a moment. R is fine here, but I am gonna add a superscript or an exponent, as those math people say. As R gets smaller, the fraction gets bigger, so the gravitational force gets bigger. All right, upon what else does it depend?
And R represents
The center to center distance.
of the radius.
Yes.
Would it matter how large or how much mass the other object has?
It does matter. So it depends on the mass of an object.
Is that the only mass component?
It is not.
Would it be M2 minus M1?
All right, so first off, what can you tell me about these two forces right here?
They're equal. They're equal forces. They're forces that are equal.
That doesn't work in this case.
Okay.
Why are these forces not equal?
Okay.
Are they like one's 1 and the other one's -1?
Yeah, opposite directions.
Um,
All right, so what else can we say about them other than opposite directions?
their magnitude's equal.
There we go. Newton's third law. All right, so it doesn't matter which object is which. So this magnitude of this force is that force from his point of view. I don't know why I'm making it a male, but from the sun's point, oh, that's why. From the sun's point of view, the earth is the other object. From the earth's point of view, the sun's the other object. So the other objects, both objects have to be taken into account, and because it doesn't matter the order in which I do it, the commutative property should hold, so no matter what I do, it should get the same answer. Subtraction does not hold for the commutative property. 2 minus 1 is not the same as 1 minus 2. However, what does hold for the commutative property,
Addition.
and
Addition.
and that's the other one, yes.
But if I kept on going, it would have been multiplication.
Okay.
Addition. That's
But it didn't say banana. And it happens to be multiplication. And for whatever reason, M2 will come first. It doesn't matter which is which. Now, the last two bits require either having seen this before or an incredible amount of insight. One of which is, it depends upon the unit system you're working in. Because the units of mass could be slugs, kilograms. Those are the two main systems, and then you can get into variations of that. And then the mysterious pound mass, which is not really a mass unit.
What is a slug?
That is in the US customary system, that is our unit of mass. If you take your weight in pounds and divide by 32.2 feet per second squared, you have how many slugs you are. So, this is a unit conversion. This is known as the gravitational constant. This one is constant. Now, I don't think it shows up as much as it used to, or it possibly doesn't show up at all, but I'm gonna put in parentheses universal gravitational constant. Now, is it universal? Well, the current theories is it's not necessarily. We don't know. We can find this value for here. We can do experiments in space. We can confirm that the gravitational constant seems to be pretty constant where we are right now, but is it the same in a different galaxy? But it's still called constant. So it's a gravitational constant, and this is one of the reasons I get really picky about the gravity. Again, big topic. There are three things that students often call gravity. This is one, little g is one, and weight or force due to gravity is 1 or 2, depending on how you want to count that. Now the other bit, imagine I've got a universe here into which I put a mass. It's just sitting there, minding its own business. And since I've created this universe, I'll put another mass in there. What's gonna happen now?
Now they have to occupy the same space.
Depends on what you meant by that. Yes or no. I have two masses, what will happen?
One will pull the other, or will they both pull each other?
They should both pull each other. Now, here's the $1 million question. How does one mass know the other one exists? It looks around with its eye of Sauron and goes, ooh, there's another mass there.
Well,
Up
does
to
it
the
need
dark side.
to know that it's there?
Pardon?
It just kind of does it. It doesn't need to know there's something there. It doesn't think about it. It doesn't think. It's a rock.
Okay, so if you're going with it has no intelligent thought whatsoever, it still has to somehow know there's another mass. Because I'm sitting here all by myself, no thought in my head, in a universe, nothing else exists, and suddenly I feel myself being drawn some way. How does that happen?
Well, if you're already being pulled, I guess you assume there's something else out there?
Yeah, but why would I know to be pulled at all? Because I'm pulling it also. Suddenly, mysteriously, I'm being pulled in some direction. Now I might be able to go, oh, there must be something over there. But it's not like the spidey sense tingles. All right, so one speculation is this thing called fields, gravitational field. Gravitational field that idea is that this is giving off something, and I'm probably the only one who's gonna call it this, something like gravitational pheromones. It gives this off into outer space, and another mass comes along and goes, ooh, pheromones. It's stronger in that direction, so let me head over there and see what's happening. Meanwhile, it's giving off its own pheromones, and so at some point it's gonna go, ooh, pheromones, oh, it's stronger in this direction, and they'll come towards each other. So this is the idea of a field. It's something that will exist just because you have one mass and the other mass will sense the field. It doesn't know there's another mass there, all it knows is that there's this field. Another idea, and not necessarily separate from the field, but they give off something other than this field, for instance, a graviton. That mass one is sending out gravitons out in all directions. And it senses the gravitons.
What is a graviton?
A graviton is a massless particle, theoretical massless particle that is basically given off by a mass. I know that's vague. It is theoretical.
So it's like, I guess a byproduct of gravity? Like created
Yeah,
by
it's,
gravity?
it's another small aspect of gravity. So if it gives off, and so you can treat gravitons as a particle, in which case you call them gravitons, or you can treat it as a wave, in which case you call it a field. That wave-particle duality is something that shows up at the end of 152. Potentially, depending on how much time we have. All right, so if I'm going with this giving off gravitons, I got this mass here, giving it off in every direction. Because it's not like it's not like a radar where it goes, ooh, I gotta concentrate in this area. No, it just gives off in every area. Every direction, coming out also. In essence, it sends out a pulse of these things, and then it gives off another pulse, and then another pulse, and then another pulse. Well, let's think about that. This is what the sphere right here is sort of a pulse